Alright, so let's do this problem. I want to find the slope at A, which is here, and I want to find the displacement at the midspan. So two different locations. So what's the first step that we always do when we're doing conjugate? Well, we're going to do conjugate beams. Well, let me ask you this. Can we do direct integration on this? Possible. It's possible. But with these point loads, probably conjugate beam would be equal or slightly advantageous. So let's try that. So in order to draw the shear moment diagram to get the moment for the conjugate beam, we're going to have to do some analysis here. So let's come over here to A and assume positive shear at A and positive bending moment at A. And I should be able to find those. I'll just use that as my free body diagram. That's a little sloppy, but we'll do it anyway. So now we'll sum moments about A. Make sure it's in equilibrium. So summing moments about A with right-hand rules, my sign convention for my statics, what kind of moment is this, positive or negative? It is negative. And about A, these two 8 kilonewton forces, what kind of moment do they create? Negative. I'm just going to stick them together. So there's a force of 8 kilonewtons. The first one has a moment arm of 2 meters, and the second one has a moment arm of 4 meters. So from that, I can solve for my moment at A. It looks like it's going to be negative, what? 48. 8 times 6, right? And that will be kilonewton meters. And then we can quickly sum forces in the y direction. Make sure it's in equilibrium. I'll assume up is positive. So my shear force acting up is positive. And my two 8 kilonewton forces acting down are negative. So therefore my shear at A is 16 kilonewtons, and it's positive. So let's draw a quick little template here and draw our moment diagram. So there's our positive X, positive shear. All these values will be in kilonewtons. So what is the shear at A? 16. Positive or negative? Positive. So we'll start at positive 16. Over the first 2 meters, the change in shear is the area of the load curve, which is none. Oh, I forgot to add something's going to happen here in the middle. So we're going to stay 16. As we go from left to right under this 8 kilonewton force, how much is our shear change?
Negative 8.
The change is 8, yep, and the load is down, so that's negative. So 16 minus 8 is 8. Change from here to here is the area of this part of the curve, which is 0, so it stays 8. And the slope is 0 because the load is 0. So there's our shear diagram. Now we'll draw our moment diagram. So there's my positive x-axis, positive moment. These will all be kilonewton meter. So what is the bending moment at A? Negative 48. What's the bending moment at this free end? Yeah, it's 0. So we better hit 0. Now remember, the change in moment is the area of the shear diagram. So it looks like that's a convenient area. It looks like 16 times 2, which is 32. So what's 40? Oh, that's negative 48, sorry. And you add this positive area to it, 32. What do you get?
Negative 16.
You get 16. Of course, this curve between these 2 points is the slope of this curve is given by the shear, and the shear is constant and positive, so the slope will be constant and positive. The change in moment from 2 to 4 is there in the shear diagram, which is positive 16. So negative 16 plus 16 gets us to 0. That's great. And the slope of that curve is given by the shear, which again is positive and constant and has a value of 8. So there's your moment diagram. Got kind of a trapezoidal section here and then a triangular section there. So these are different slopes, right? If we looked at these carefully, it would be, this would be 16 and this would be 8, given by the shear. Any questions about that? All right, so let's draw our conjugate beam. Now remember, the conjugate beam, we don't care what the load is, we just care about the geometry. So what's our conjugate beam going to look like? So a fixed connection in conjugate space becomes free, and a free becomes fixed. So we're going to just flip it around. It's going to look like that. Now what I like to do is just take my moment diagram and just lump it right on it. So I'm going to do that. Now this moment is positive or negative?
Negative.
It's negative. So what is a negative force, up or down?
Down.
Down. So this is going to be down. Remember, it's the moment divided by EI, so this particular value here will be 48 kilonewton meters. That's the moment divided by EI. And this value will be 16 kilonewton meters divided by EI. Just to remind you, this was point A originally. It stays that, and this is point B. So we're looking for the slope at A.
And it's 2 meters.
That ain't gonna work. Why would I put slope at A? What's the slope at A? 0. Dumb. I don't think I meant that. I think I probably meant the slope at B. Yeah, because if I asked you the slope at A, you wouldn't have to do anything. Just write down 0. Why? Because it's fixed connection. Yeah, I think that's a mistake. I'll fix that. Let's do that right now. Let's say it's the slope at B. I like that better. Well, it's more work, but it's better for us. And then we want to know the displacement at the midspan, which would be right about here. So what should we do? Since I've changed the problem to be the slope at B, then I need to probably find the what at B in the conjugate beam? The shear. So shear at B positive is down. We don't need the displacement there, but we could get it, and that would be the moment at B. I'm not asking for the displacement at B, so I don't really care about that, but we'll probably need it. Maybe we might need it for something else. We'll have to see. But for right now, we can get the slope at B. So to do that, there's going to be a lot of bookkeeping involved here. And I'm going to break it up into 3 different forces. Force 1 for this triangular area. Force 2 for this kind of rectangular area here. And then force 3 for this triangular area. So if I can get those 3 forces, then my shear is just going to react to balance them. So that shouldn't be too hard to find. But it will take a minute to get those forces. So I'll start here. Let's see if I can do this. The force in 1. So it's a triangular, it'll be base, which is 2 times the height. And what's this height here of the triangular portion?
32.
Yeah, because it's 48, but this part here is 16, so it's 32. So it's going to be 1/2 the base, which is 2 meters, times the height, which is 32 kilonewton meters, divided by EI. That's an easy one to compute. The 1/2 cancels the 2, so it's just going to be 32 kilonewton meters squared divided by EI. F2 is what? Well, it's a rectangle, so it would be the base times the height. The base is 2 meters, and the height is 16. So that's 2 meters times 16 kilonewton meters divided by EI. That's also 32, conveniently. And then F3, this triangular area here, so 1/2 times the base, which is 2 meters, times the height, which is 16 kilonewton meters, divided by EI. And again, conveniently for us, the 2 meters and the 1/2 cancel, so that's 16. So those are pretty easy to calculate. So now if I want to find my shear value and the slope, I'll just sum forces in the y direction, make sure it's in equilibrium. So what do I have in the y direction? I'm assuming up is positive, so all my forces as drawn here are negative. So I'll have negative the shear at B minus F1, which is 32 kilonewton meters squared divided by EI, times F2, which is 32 kilonewton meters squared divided by EI, times it, plus F3, which is down, which is 16 kilonewton meters squared divided by EI. So it looks like the shear at B is equal to whatever that is. What is it? That sounds reasonable. So that would be minus 80 kilonewton meters squared divided by EI. Now, in this particular problem, you'll notice that EI is not given, so you just have to leave it. You're done. So the only thing you can check at this point is the sign. So if you go back and look at the original problem, you can probably guess that the structure would do something like this. And that the slope at B, if you look at it, is negative. So at least the sign matches. Questions about that? Now, if I want to finish the problem and find the displacement at the midspan, I'm going to need to cut my structure at the midspan and decide if I want to do the left side or the right side. Decision. And this is one we can think about for a second, and if you get this problem on the exam, let's examine the right side first. Well, I've already gotten the reaction shear, but I don't have the reaction moment. So I'd have to get the reaction moment. I've already got F3, so I'm ready to roll. If I did the left side, what do I have to get? Nothing. I've already got F2 and F3. I just find the moment and I'm ready to roll. So I'm going to do the left side. So we'll come over here and draw a free body diagram of the left side, which looks something like this. And I will go ahead and label the internal positive moment. And just to make it match here, I'll kind of redraw the shape so that you can see what I'm doing.
This is just extra, right? This doesn't have to do with the question.
Well, the question asks the displacement at the midspan.
Oh, displacement at the midspan.
Remember, displacement in the real beam is moment in the conjugate beam. Now, in terms of calculation, we've pretty much done this already because this is still force F1. This is still force F2. One thing I want to do is come back and compute those distances from the cut to F2 and from the cut to F1. So F2 is D2 is easy. What is that? That's just half the distance. The distance is 2. That's just 1 meter. What about D1? Yeah, it's 2/3 the distance, right? So 2/3 of 2 is 4/3. And I'll just leave it that way. I won't have to carry around the fraction. Well, I'm going to carry the fraction, not the decimal. And then all I have to do now is sum moments. So we'll sum moments at the cut and make sure we're in equilibrium. So when we do that, with this sign convention for my statics equation, this moment is positive or negative? Positive. So there's the moment. Force F2 and F1 create what kind of moment about the cut? Positive or negative? Positive. So it would be, we'll do F2 first, F2 times D2. Well, F2 was 32 kilonewton meters over EI times D2, which is 1, plus F1, which is also 32 kilonewton meters.
Are they squared?
They're squared. Yeah, I forgot. Yeah, they are squared. I was about saying my units aren't working out. Thank you. And then times that moment arm, which is 4/3. So what's the moment? Looks like the moment's going to be negative. 52. You got what?
74.
That seems reasonable. 74 exactly?
0.67.
Oh. 74.67, and that would be kilonewton meters cubed over EI. And again, we don't have values for E and I, so I don't have to worry about that. But we can do one quick check. It came out negative. Would you expect the point here in the midspan to go down or go up? Down. Down is negative. So that seems reasonable. So any questions about this one? No. All right.